Hi. So I'm gonna tackle a couple of other problems from chapter four in this excellent book by Purcell. So the beauty of the problems that he made up in his book is not only that these problems are of highly practical value, but they're really a lot of fun to try and solve because a lot of the problems are a good mixture of both an intellectual brain teaser and also of pragmatic utility. And I think this is another pretty neat example where both qualities are required to solve the problem within a realistic time frame and also a realistic effort frame. Okay, so here's the deal. We have this tetrahedron network of resistances. So every line you see is a resistance. So there will be altogether six edges or six resistances. Each has the same resistance value. Let's call that R. And then there's some voltage that has been applied between point A and point B. These are the two vertices of a tetrahedron. And of course, due to that voltage applied, there will be certain current flowing from A to B, like this. And let's call that current I1. But since this is a network, there will also be some current flowing through the other channels, like this edge and that edge over there, and then this edge, which is not visible uh, from this angle, and through this edge to reach B. So there are a couple of other sort of conducting channels through which you can put some electric current from A to B. And the question is, what is the effective resistance? In other words, what is the exact amount of current that flows from A to B under a voltage value of let's say V applied between point A and B. Okay, so that just amounts to solving a couple of loop equations for a bunch of triangles, I guess. So there will be, let's say, how many faces are there? There are four faces altogether, so presumably you can write down four different loop equations and try to solve them without making mistakes. However, I can be a little bit more clever and invoke some symmetry idea. And the symmetry idea is something like this. Okay, so tetrahedron is a highly symmetric object, right? So if the current that flows along this edge were I2, that's the amount of current that flows along this edge, then there's no other choice but to have exactly the same amount of current flowing through this edge that I drew in terms of dotted lines, right? Simply because these are just identical from the geometric perspective. Since these are identical edges, and there's no way you can put more current on one edge than on the other. Okay, so this gotta be I2 on both edges. And then it also dawns on you that along this edge, you simply cannot have any current, right? Because if you have some current going this way, then by geometric symmetry of this tetrahedron network, you must expect exactly the same current going the other way. Okay, that's a conflicting requirement. And the only way to resolve the conflict is by taking none, thereby allowing no current to flow along this edge. Okay, that seems to be the only symmetry allowed value for the current along this edge. Okay, I mean, of course, you can verify my claim by solving all these loop equations, but when the symmetry argument points you toward an obvious direction, then there's no real need to waste your effort trying to prove the obvious. So here I just write down this answer as obviously true. Okay, but then that leads to another very obvious consequence. Since the current that comes in through this edge cannot possibly flow along this edge, then all that current must be deflected upward through this edge to go to B. Likewise, the current that flowed along this edge, the hidden edge, must also get entirely deflected and start flowing along this edge and arrive at B. Okay, so there are these four edges here and here and here and here that simply by virtue of symmetry and current conservation must carry exactly the same current. And I call that value I2. Okay, so suddenly the problem is several times simpler than what we might have expected at the beginning. And also you realize that there are three different channels now of conduction that would carry current from A to B. Excuse me. And that's this channel, which has the resistance R. And I drew that symbolically as a single line over here. And also there is this longer channel consisting of two resistors. There's one resistor over here and there's another resistor over there. So since these two resistors are connected in series, the effective resistance is twice R. Okay, and I have drawn this as this semi-elliptic curve over here with some current I2 flowing along that. And there's another semi-elliptic curve through which the same current flows with the effective resistance of twice R. Okay, so at the beginning we started out with this three-dimensional resistor network. But then we were able to immediately reduce that problem to that of some two-dimensional resistor network like this. Okay, and this is pretty simple to analyze if you think just a little bit about it. Since the voltage drop from A to B must be the same no matter which path you choose to follow. So therefore, since the resistance on this side is twice as big, so then the current must only be half as big, because then their product would be the same as the other channel. Okay, so you have half of I1, you have full I1 current, half of I1 current. Okay, so altogether, the current flows through these three different channels is obtained by adding up all three contributions equaling twice I1. And after solving some obvious relations, you come to the conclusion that the effective resistance between A and B points of a tetrahedron is half of the single resistance value. So what that implies is that if you have a resistance network like this, then exactly half of the current flows directly from A to B, and the rest of the other half of the current flows through the more indirect channels. Okay, so that's a kind of fun way of reducing this tetrahedron network problem to a two-dimensional planar network problem. And maybe you can just view this tetrahedron thing right from the beginning as a two-dimensional network. Because when you view this tetrahedron network from the top, this is really what it is. Okay, right? And then this is A, this is B, and you're connecting the two nodes with some EMF, and therefore there will be some current going through all the edges. Again, just by looking at the symmetry of this whole thing, okay. Yeah, maybe I should slow down a little bit. Okay, so first of all, let's look at this big triangle over here. Okay, and then the loop equation. No, not a loop equation, but the Kirchhoff relation would read as follows: that the EMF must equal these I1 times R, but I have taken R to be 1 for simplicity. So the voltage drop across this edge is I1 times R, okay? And the voltage drop across this edge is I3 times R, and across this edge is also I3 times R. So altogether, the entire voltage drop equals this thing, and that's equal to the EMF. But you can also work out the Kirchhoff rule for this smaller triangle. And all you have to do is just replace I3 by I2 over here. So then just by identity of these two equations, you conclude that these two currents must actually be the same. Okay. And why was it that I was able to set both of these current to be I3? That's again coming from symmetry, right? Because this geometrical shape is symmetrical and the resistance on each edge is the same. So by a simple symmetry argument, then you must conclude that there will be same amount of current flowing along this edge as along this edge. Okay, and then we just proved also that these two currents have to be the same. So this current is the same as this current. Now, and therefore, since you have the same current flowing along this edge as along this edge, then this edge cannot possibly carry any current. that would be, otherwise you will be violating the current conservation at this node or at this node. And therefore, I4 is 0. There's no other choice. And then after just one more line of writing some equations, you will reach exactly the same answer as we got here. Okay? So, although at the beginning we seem to have faced a pretty horrendous resistor network problem, if you can just hold your own and stare at the problem for a little while, then some symmetry argument starts popping into your head and drastically simplify the problem down to a pretty trivial level. Okay, so I hope that was a fun exercise for you. Okay, number 2. So here's another pretty fun intellectual problem that I actually never had the chance to think about before, but thanks to this opportunity, I'm glad that I was able to um, share my understanding of this problem with you, besides just being able to learn about it myself. Okay, so the setup of the problem is really simple, and this is something that we've been talking about ever since I guess physics classes in high school. So the problem is the following. Suppose that you have a fully charged capacitor. So you have a stack of positive charges on one side of the capacitor plate and a stack of negative charges on the other side of the capacitor plate. And they're not able to discharge themselves because the circuit is open. The switch is flung open, so there's no way that the charges will be able to flow out and discharge. Now, you close the switch, and then of course there will be a discharge. So the positive charges over here will start flowing along the circuit, annihilates the negative charges that were sitting on the other side of the plate. Or vice versa, negative charges travel all along the circuit and destroy all the positive charges on the other side of the plates. However, we kind of pretended that this is something that would have to happen without thinking too much about how this might happen. Okay, so this is where this brain teaser of a question begins. Because we were taught actually that if you have a parallel plate capacitor charged with equal but opposite amount of charges, then the electric field just outside the capacitor plates is 0 because the electric fields coming out from each plate are going to cancel each other out. Well, if that were the case, then there's no electric field along any segment of this line circuit, and we don't have any battery here, and so there's no independent source of power to drive the electrons around along the circuit. So without any electric field and any EMF to power the electronic motion, how are we supposed to create the movement of charges from one side of the plate to the other? And if there's no electric field anywhere along the circuit, and therefore the electrons do not move, then even after you close the circuit, charges will continue to pile up here. Opposite charges will continue to be sitting on this plate, and they will never be able to discharge. And is there a flaw in the argument that I just presented? Well, if there's no flaw, then what I said just must be true. And you will never be able to discharge a capacitor even if you close the circuit. But that seems unrealistic, and that's probably wrong. So it's our job to try and scientifically prove just why is it wrong and how to get around this apparent paradox. That's what we do as scientists. We encounter a statement that seems to violate the common sense, but we look hard at the problem and figure out that there is a loophole in this paradox. Okay, so we're going to find out a way to defeat this paradox. And the first step in such a battle against this false paradox is this obvious realization that because the electric field is a conservative field, at least the static electric field is a conservative field, and therefore the voltage difference between this plate and the other plate, due to the charges that piled up here and here, must be achieved by making a line integral from one plate and follow some path which extends outside of the plate and arrive at the other plate. Okay, so if I choose such a path and perform this line integral, then the result has to be equal to the voltage difference between the two plates. And there's no way, absolutely no way, that you can get around this very general, very broad conclusion. Okay? So, of course, this is obviously true if you did the line integral directly from the one plate to the other. Okay, because then you know that there is obviously an electric field trapped inside the capacitor plates. And so then the result will be just the electric field, which is typically uniform, multiplied by this separation S. So electric field multiplied by S is equal to the voltage difference. But the point is that even if you took a different path of integration, let's say start from here and go out over here and then come back to the other plate, that must also give you the same result, V, for the line integral. And this cannot be done unless there is some electric field somewhere on the outside of the capacitors. Okay, I mean, first of all, the usual notion that electric field is entirely confined between the plates, that's only true if the capacitor plates were infinitely big. Okay, if the area of this capacitor plate were infinite rather than finite, as in real life, then it's true that electric field is entirely trapped in this little space between the plates. However, in real life, of course, there's no way that you can create such an infinite size capacitor. So the finiteness of the capacitor must come into play somewhere, somehow. And also, if the capacitors were truly infinite, then there's even no way that you can attach a circuit around it like this, because then you would be just cutting through the infinitely large capacitor somewhere, and that wouldn't be much of a circuit. Okay, so now the focus should be on how the finiteness of the capacitor plates would come to the rescue and bring us to the conclusion this integral will be finite after all. So here I have drawn a little diagram, rather dense diagram, but this is the side view of the capacitor plates, which has a finite dimension. It's not an infinite capacitor. With a bunch of positive charges on one side and a bunch of negative charges on the other side. And there will be electric field directly coming from the positive charge to the negative charge like this. However, once you go outside the interior of the capacitor, the electric field does not die out immediately. It kind of leaks out like this. Okay? Now, then think about making a loop like this one and follow this loop to perform this integration. Okay? Well, first of all, along this side and along this side, there are two possibilities. Either you have no electric field because these positive and negative charges tend to create opposite signs and opposite directions of the electric field. And furthermore, if there were any electric field, then the direction of that electric field will be most likely orthogonal to the path direction that you have chosen. So electric field, if any, will be pointing in this direction, whereas you're integrating along the path in this direction. And because the two directions are orthogonal, the line integral will pick up nothing. And also, the line integral along this path will pick up nothing. However, the line integral along this path, along this small portion over here, will pick up something, right? Because both the path direction and the electric field direction are parallel. And also the magnitude of the electric field just outside the capacitor is more or less the same as the electric field size inside. Okay, so then you can easily imagine that here your line integral will be roughly the product of the electric field multiplied by the separation of the two capacitor plates. But that's exactly what we can equate with the potential difference between the plates. Okay? So now it seems like the paradox is gone. But just to make sure that we're not tricking ourselves into believing that what we are saying is right, let's try and consider maybe another path. This time, we're going to choose a path which is consists of a very long straight line in a very large semicircle of radius r. And eventually we're going to take this r to go to infinity. And another very long straight line segment which reaches the bottom half of the capacitor plates. Now, the reason why I have chosen such a big path for the line integral is that when you view it, the whole thing on such a large scale, then this capacitor plate looks pretty much like a simple dipole. Okay, you have some accumulation of positive charges here, accumulation of negative charges over there, and that's a dipole. And we know that the dipole creates an electric field that falls off as the distance cubed. Okay, and so therefore, regardless of which direction the electric field may be pointing, the line integral of the electric field performed along this big semicircle is going to be on the order of inverse r cubed multiplied by the length of the integration path, which is r, and that's just 1 over r squared, and 1 over r squared goes to 0 as r goes to infinity. Okay, so it's pretty clear that the line integral contribution from this large semicircle is going to be 0. However, what about the contribution along this straight line? Of course, if you go far out along the straight line, again, this sort of scaling thing kicks in, so there will be little contribution to the line integral. But also, this line, this straight line comes very close to the point of touching this surface of the capacitor. So therefore, maybe in this nearby region, there will be a non-zero contribution to the line integral. Okay, so the quick estimate is that this dipole electric field strength, which is the dipole moment divided by the r cube, integrated along this line integral element, starts out at s and goes out to infinity, will give you a value which is something like a dipole moment divided by s squared. And then according to an independent estimate, you can probably prove that this dipole moment scales as s to the third power and multiplied by the electric field. And therefore, the overall result is the electric field multiplied by the this separation between the plates. Now, here I have given an extremely hand-waving argument, but I think you can prove that actually the dipole moment of parallel plate capacitor is in fact some charge density multiplied by s to the third power. That would be my guess. And therefore, the overall result for the line integral is this thing, which again equals the voltage. So the point is that whether you choose a very, very tiny integration path like this, or very, very huge integration path like this, in either case, the consequence is that you will always pick up the same value equal to the voltage difference for the line integral of the electric field. So the bottom line is that there has to be an electric field somewhere on the outside of the parallel plate capacitor. And therefore, there will have to be some electric field affecting the electrons along the circuit, and that's what sets the electrons in motion and sets up the discharge. Okay? So I hope that was convincing enough for you. Okay, now we come to the main event of this week's lecture, which is the proof of this thing called the Thevenin theorem. So we, as a physicist and maybe some engineers, we're kind of scared. It's normal for us to get a little bit scared when we see the word proof or theorem, because we're much more accustomed to playing with examples than making proof of some abstract theorem. But in my personal view, proof is what happens once we have seen enough of examples and start to get sick and tired of playing with more and more examples. So what I mean is that after making concrete and plausible observations based on a number of examples, a generalization of some sort begins to take shape in your brain. And then you start wanting to formulate that into proof. Now, the other aspect of that statement is that when we say we want to prove something, as engineers and physicists, it's often sufficient to prove it with a sufficient example. And if the example that you use is of sufficiently general nature, which is, of course, a somewhat subjective definition, then even the proof in the case of a single good example is enough to convince you that this must be true for all circumstances. Okay? So without delving into the most general possible situation, I'm going to present the proof of the Thevenin theorem with one rather good example, which is shown here. So what's shown here is an electrical circuit consisting of a fairly complex attachment of voltage sources. Here I have three different voltage sources, E1, E2, E3, and a couple of resistors, R1, R2, R3, R4. And then I create these nodes, which I then connect to another external voltage source with voltage epsilon here. Okay, so without explaining in detail exactly what it is that I want to prove under the name Thevenin theorem, I will just write down all the obvious loop equations that will be applicable to this particular arrangement of resistors and voltage sources. Okay, so here I have three loops which are independent. And through each loop, I can assign a certain loop current. I call I1, I2, and this one I call I. So these are going to be the three unknowns that I want to solve, which means most likely I will end up with three different equations? Well, that's obvious because you have 3 loops and each loop gives you an equation, and so there will be 3 equations in total and 3 loop currents, which are the unknowns. Okay, so in this way, you can kind of obviously convince yourself that the number of loop current variables and the number of equations must always go hand in hand. There must always be the same number of equations as there are loop currents. And therefore, you can always solve that problem. Okay? So this is a kind of abstraction you can easily make without trying to cook up a formal argument. So I'm going to start writing down the loop equations one by one. For this loop, for example, I have this equation. Each term is something you can just read off by looking at these different components of the circuit that forms this loop here. And for this loop, I have this equation. And for this loop, finally, I have this equation. Okay, so this is a bunch of linear equations. But because this is a linear equation, and also because the variables that we want to solve, well, I mean, let's just kind of saying the same thing over again. So maybe let me not say it. Because this is a linear equation, it means that we can cast these equations as a matrix equation. And you can easily show that these 3 separate equations can be cast as a single matrix equation, like this. Okay, and therefore by taking the inverse of this matrix, I cannot find my cursor. Okay, here we go. Okay, by taking the inverse of this matrix, then you can express this current vector in terms of some inverse resistance matrix multiplying the EMF vector. Okay, so now what's remarkable about this matrix form is that there's a complete separation of all the variables corresponding to the current, all the variables corresponding to the EMF, and all the variables corresponding to the resistances. And this is not just a lucky coincidence that happened for this problem. This is the kind of thing that will happen for any problem consisting of arbitrary number of resistances, arbitrary number of EMFs in whatever manner of connection for the resistances and EMFs. It doesn't matter. This general structure of the resistance matrix, consisting entirely of the values of the resistance and nothing else, acting on the current vector, consisting of um, of the values of the current, of values of the loop current, equaling the EMF vector consisting only of all the EMF values, this general structure can never be violated in any electrical network problem. Electrical network problem consisting only of voltage sources and resistances and nothing else. So we're not including any capacitors or inductors into the playground yet. Okay. Now, once you come to this realization, actually the proof kind of falls into your hands automatically, because what that means is that in particular, this value of the current that flows to the external connection, that's what we call the I, that is also a function of rather the linear combination of all these EMFs, which means I can express this current through the external connection as a linear combination of the external EMF and all the other internal EMF values. And I'm going to have to introduce some coefficients, A1, and whatever. But these coefficients are the elements of this inverse matrix element. But since the original matrix element consisted entirely of the resistance values, its inverse matrix also consists entirely of the resistance values. And therefore, each coefficient over here consists entirely of the resistance values. So none of these coefficients will involve expressions like epsilon or I or anything. It's only a function of the internal resistances. Okay, so now I'm gonna divide this equation by A, which will then give me this. Okay, so this is a simple rewriting of the previous equation after dividing by A. Now this equation has the general structure of the epsilon, which is the EMF of the external source over here. And here's everything else, right? We don't know what this is, but we can just call it epsilon equivalent. And that equals I over A, but this inverse of A I'm going to call R equivalent, so that the final equation takes this simple form. Okay, so what's the meaning of this? Well, the meaning of this is that we have this thing coupled to some black box of an electrical circuit. We don't know what's inside this shaded rectangle, but what we do know is that if I hook up this voltage source of epsilon to the black box, then I measure the current equal to I flowing through my measuring device. Okay, and between my external EMF and my measured current, I discover that this relation exists. So it's not simply epsilon equal to I times R. There's something else in here, which means that even if I do not attach an independent power source over here, I can still measure some current flowing through my measuring device. And of course that makes sense because internally inside this black box, there may be its own power supplies. I mean, batteries and current generating sources. Okay? So whatever EMF that this black box is providing to the attached circuit is what's captured by this value of E equivalent. Okay, so this is essence of the Thevenin theorem. What it says is that no matter what the black box consists of, you can always write down the situation in terms of this single equation. And all the details about the black box is captured by these two constants, R equivalent and epsilon equivalent. Okay, so that's the essence of the theorem. Now, how do we actually determine what these epsilon equivalent and R equivalent values are? Well, in practice, this R equivalent equal to 1 over A, where A is this coefficient used in the expansion of the solution for the current, only consists of only depends on the values of the internal resistance, which means in this example, this R equivalent is only a function of R1, R2, R3, and R4. It can never be a function of epsilon 1, epsilon 2, and epsilon 3. Well, then what that means is that even if you consider the situation where all three epsilons were turned off, that is, if all three epsilons were 0, and then try to calculate what R equivalent was, you will still get exactly the same value. Which means you can avoid the complication and simplify the problem a lot by taking these epsilons, all three epsilons to be 0. So then this epsilon vector will have elements equal to just epsilon and 0 and 0. And then you take the inverse matrix and work out this matrix multiplication and so on, and obtain this value for A, while everything else will be 0 because you have taken all the internal EMF values to be 0 in this case. And whatever you get for A will be giving you the R equivalent. Okay? So that's how we obtain the R equivalent for the circuit hidden in the black box. Now, what about epsilon equivalent? Well, once you have found R equivalent already, therefore you know what this is, then epsilon equivalent is obtained by taking epsilon to be 0. Okay? So now what that means is that in this problem you choose epsilon to be 0, but keep epsilon 1, epsilon 2, epsilon 3 as finite. Okay? and then do the matrix inversion and so on. And that way you will be able to obtain what this equivalent EMF is. Okay, so I hope you enjoy the proof, which is a rather pragmatic proof of Thevenin's theorem.